So good evening, everybody. Thank you so much for coming. I'm going to be talking today about the fundamentals of data mining and the open software question. The first thing I'm going to do is just quickly give you an introduction to me, because it will give you an idea of where I'm coming from. A long time ago, I was an academic. I was a specialist in AI and taught many things, including machine learning. For some time after that, you'll see from the dates, quite a few years, I was in the commercial software world, and in particularly commercial data mining software. And some of my comments you may trace back to that. But for the last few years, I have been a freelance data miner. And that has broadened my outlook a good deal, hence the ideas that I'm going to present today. I also want to talk briefly about something that I have started in my freelance years, the Society of Data Miners. This is a new professional body. Our aims are to bring the practitioner, the analytics practitioner community together as a true profession and raise awareness and widespread understanding of our practice, of our field of data analytics. All of which we believe will really improve the benefits to society. We get a lot of benefit out of analytics already, but we could be getting so much more. If you're interested in knowing more about the Society, you can find us at this website. We're also on LinkedIn. We have a group. You'll find us on Twitter. And there is a meetup group. We do regular events. Okay. Now to the particular subject matter of today. I love giving talks like this, and the reason is it gives me a chance to put down on paper things that I've been thinking about. So this one in particular, these are some ideas that I've actually been using for quite some time, but haven't put them down on paper before now, which has both pros and cons. You know, the pro is, well, this is fresh and new. The con is there's probably some rough edges, particularly about this final part. But the outline for today is, first of all, I'm going to talk about some ideas about the fundamentals of data mining. What's really going on when we do data mining or data analysis in general? And based on that, I'm going to talk about a way of understanding the differences between different software packages, because you have probably all seen that in data analysis we have a wide variety of options to choose from: commercial, open, different kinds of software, and it can be a bit confusing. Hopefully I'd like to put those things into context. And finally, I'm going to suggest a direction for open data analytics software, and you'll see what that's about when I get there. So first of all, the fundamentals of data mining. I'm going to say a few words just about the wide variety of things that data mining and data analytics are used for. I would say that probably the most common application of data mining is in understanding customers. So commercial organizations want to understand their customers, essentially to do better business, do more business, make more money, make a living better. They ask questions like, who are our best customers? How can we get more like that? How can we stop them leaving? And so on. I don't want to spend too long on each section. You can appreciate that probably each bullet point here is an hour's lecture, or possibly many. Also in the area of understanding customers, how they behave, particularly there's a lot of behavioral data now in the internet age, and understanding that is a kind of extension of the more traditional customer understanding that people have done. And more recently, content mining. There's an awful lot of electronic content out there that people are generating all the time, and understanding what they're saying, not just how they behave in commercial or other ways, is important to organizations. Not only for commercial purposes, of course. For example, a government organization might want to know who uses their website in order to understand how to give out better information or give it out more effectively. Perhaps the second most common type of data analysis would be in the risk area. Risk analysis in general, and I'm talking about all kinds of risks, not just the kinds of risks that banks want to or have to measure, but also things like any kind of organisation that might be a victim of fraud, might be interested in detecting fraudulent transactions, that kind of thing. So all kinds of risk analysis probably make the second most common application of data mining. What I've done over on this side of the slide is just list a whole lot more interesting ones, ranging from law enforcement, things like detecting money laundering, detecting network intrusions. Wind turbine maintenance was just one I ran into and rather liked, predicting when wind turbines are going to break down, and more generally with any kind of industrial process, optimizing it or improving its quality. Data mining is used to help with the environment, to manage the environment better. I remember a project about trying to understand what happens to endangered species when you introduce them into new environments, that kind of thing. A whole range of medical and life science related applications, ranging from drug discovery to medical research more generally. And the last one, I just put that in because I kind of liked it. This was a project where they wanted to detect whether the label on a wine bottle was telling the truth. Is the thing in the bottle really the wine that the label says? And they used data analysis to help them detect fakes. So there's a wide range of different applications here, and I'm talking about the tools that are used for all these kinds of things. Before I get onto the tools, I want to talk just momentarily about the process, because it is one of the fundamental things to understand about data analytics. There is a process. Most analytics practitioners actually use the same process, but not all of them give it the same name. This is from a project that built what was intended to be an industry standard methodology for data mining called CRISP-DM. And what we found when we talked to a wide range of practitioners was that they were actually all using more or less the same process. But it's interesting that when people write down their processes, they sometimes leave out important parts. So a key thing that we wanted to include was the business aspect of data analytics, by which I mean not just business as in commercial, but business as in the domain. This is, there's an important part of analytics, or rather, really the key to analytics is that it's founded on understanding the domain, and also how you're going to use the results, which are also a domain question. CRISP-DM breaks down the analytics processes into these 6 phases. I'm not going to go through all this in detail. I wanted to emphasize the importance of the business aspect. And the next slide really just says, I don't want to tell you all the details of this process, but there are details. It does go into quite some detail about the different parts of the analytics process. If you want to know more about CRISP-DM, there is or used to be a dedicated website. If that doesn't work, you can also find the documents on my website. CRISP-DM answered a particular question which people were asking, which, put simply, was this: how do I do data mining? Now that I've got some interesting software that I've bought from you, how do I actually use data mining to solve a problem? And CRISP-DM answered that question. But the question that it didn't answer, that has always fascinated me, is why is the data mining process always the same? Why does everybody discover the same process? Why is it? And why does it take the form that it does? And this material, the 9 laws of data mining, were an attempt to try and get at some of that. So I'm going to go through this very, very quickly. Again, you know, I could spend an hour probably easily on this, but I'm going to try and do it in 2 minutes. So these are things that all analytics practitioners know are true, but by experience, well, probably somebody will put their hand up and say, well, I don't. But that's my experience, that first of all, these are things that I've observed, and secondly, I think most analytics practitioners would agree to most of them. The fact that underlying any analysis is the thing that you want to use it for, a business or domain objective. The fact that domain knowledge or business knowledge is a core part of every part of the process. It's not just something you use at the beginning or use at the end. You use it throughout, at every stage. The fact that data preparation, getting the data into the right form, is a large part of the process. People sometimes think I've used too low a figure here, under questioning I'll explain why it's as low as it is up here. It's not what I disagree with everyone else. The fourth one is about discovering the right model for a particular application. The statement is simply that you can only discover it by experiment. The fifth one says you always find patterns in data that are related to the problem you're trying to solve. It's strange, you'd think that some data would not have those patterns, but yet it always does. Strange but true. Again, the reason is the interesting part, but I don't have time to go into it here. They're all about the explanations behind them, and if you question me carefully, I'll tell you some more. The sixth one is about how analysis produces insight. That always fascinated me. We get insight, new knowledge out of data analysis, but how does that happen? The seventh one is about the meaning of the word prediction, as in predictive model or predictive analytics, something that's puzzled me greatly because often what we do is not about predicting the future, and yet we use the term prediction. The seventh law was to help define what we meant by a predictive model. The eighth law is about value, the fact that technical measures don't measure the value of an analysis. Simple as that, a fact often forgotten by highly technical people. And the final one, the law of change, is about the fact that when we find patterns in data, we should not expect them to stay the same, because they never do. Even the ones we think will be true forever usually aren't, not as patterns anyway. So these were some principles, and I think working through them gives you an idea of the angle on analysis that I'm trying to push here. I want to particularly emphasize two of them. The first one is the one about business knowledge, that business knowledge is involved in everything we do. Every stage of the data mining or data analysis process involves knowledge of the domain, the subject matter of the data. And it has a profound impact on the tools that we use. And the second one that I want to emphasize is the one about insight. The fact that what's really going on when you talk about data analysis is that the organization that owns this data is perceiving the world through that data. The data of an organization acts like an organism's sense data. It's how organizations see and learn. I usually have this slide animated, and it's a little bit sad that we couldn't make the animations work today. But this is the final section of my fundamentals part of the talk. And I use it to emphasize a commonly believed myth about data analysis or data mining. And the myth goes something like this. You start with data. From the data you build a model, and that model generates useful actions. Or it can be, you've got a model, you feed the data through it to generate useful actions. I say that this is the wrong way to think about data mining. I don't know whose phone is ringing. That's the myth. This is the right way to think of it. It starts, the analytical process starts with knowledge. And we apply that knowledge to the data to get more knowledge. And that loop, going from knowledge to data and back to knowledge, is why the analytics process is iterative. It's an iteration between knowledge and data. And at any point, we can decide to use a combination of knowledge and data to drive action. By the way, those in the audience that are familiar with ideas about cognition and think about such things may notice that this looks very like the way that perception works, that we apply the knowledge of the organism to that sense data to generate more knowledge or usable information. and all of which helps to guide action. And that's why I talk about analytics being a form of perception. Just arising from that diagram, I found it neat that you could explain the difference between data mining and BI using the same diagram. It's quite simple, really. It's a slight oversimplification, but BI uses a fixed set of knowledge. So that's why BI systems, it's worthwhile building a big and often expensive system based on a fixed set of knowledge, because it's not going to change all the time, so that you can have a relatively stable knowledge base and apply it to successive sets of data, and the knowledge stays the same. Whereas in data mining, the knowledge is always changing. That's the whole point. And that does put constraints on the kind of systems that we generally build. Okay, so that's what I wanted to say about the fundamentals of data mining. I want to go on now to the second section, which is about understanding the differences between analytics software packages. So the packages that are used for that process that I've just been describing. And it's the fact that they're used, it's the fundamentals of data mining that are driving what I want to say about software. So in order to understand the differences between tools, I've listed 4 different dimensions. I'll tell you in a moment about which ones I'm going to mainly concentrate on, but first of all, just to explain them. The first dimension is classifying tools by, are they mainly about seeing the data, or are they mainly about seeing the process? I'll talk a little bit more in a minute about why that's important, but just to illustrate what I mean there, a spreadsheet is all about seeing the data. You see the data laid out in front of you. You see the data. On the other hand, when you write a program, you're looking at the process. The program is a description of the process that you want to be applied to the data. And that dimension, see the process versus see the data, I think is a very important one in thinking about different tools. The second dimension that I want to use is the technical versus intuitive dimension. And the reason for believing that's important is, you remember I said business knowledge is fundamental at every stage. And it does seem to me that the more technical we make our tools, the harder we make it to fold in business knowledge. It's never impossible, but the more intuitive they are, the easier it becomes, because we are able to concentrate more on that business question or business information and have to concentrate less on the technical side. The third dimension is about how comprehensive is the tool. Does it have everything you need? And so I'm going to grossly oversimplify it in this presentation and just say, yeah, it's either yes or no. Either it's comprehensive or it isn't. And the fourth is about design coherence. Is the design consistent across the tool? The different parts of the tool, do they work in the same way? Can you predict how one part is going to work if you know the rest of the tool? Or it's the design kind of all over the place. And you do find tools where the design is a bit all over the place. I'm not going to really concentrate on that one, although I will mention it for each tool I describe. So those are my 4 dimensions. I'm going to talk a little bit more about see the data versus see the process. So under see the data is visible. Interestingly, these tools tend to be relatively intuitive, in the sense that because you can always see the data, you can kind of see, you can see what's being talked about, shall we say. This is just a picture of a spreadsheet. It's not a particularly good one, but I needed one in a hurry. The difficulty with seeing the data and not the process is that for anything even remotely complicated, you can't see what's going on. So many of you, hands up, everybody who's ever had to debug a spreadsheet. Yeah, right, so you all know what I'm talking about. You can't see what's going on. It's a nightmare when it gets complicated. On the other side, the process is visible. This is an example of very clearly visible processes. But you only see the data when the data is requested. In broad terms, I mean, it can be intuitive, but it's probably not as simple and intuitive as a spreadsheet. And sometimes very much not intuitive. It's good at expressing complex analysis. It makes it easier to debug a complex analysis, which is always needed. It's overkill for really simple analyses. When you've just got a little table of data and you want a nice little graph, there is no need for this kind of thing. And even if you're going to do that same kind of thing several times, a spreadsheet is probably simpler. But as soon as it starts getting complicated, you need some way of seeing the process so that you can fix it when it's not right, and so that you can understand it at all. The technical versus intuitive dimension. So here's an example, a little bit of our code, I wrote this particular fragment a while ago, and I now think this is one of the rather more intuitive pieces of our code that I've written. Compared to this, most our code is even more opaque. Whereas in terms of understanding what process is going on, I would say that these graphical tools are a lot more intuitive. They show the process in an intuitive way. Funnily enough, these two things, purely by chance, do almost the same thing. This one's got a little bit more in it, but basically they do the same kind of thing. So given those 4 dimensions, I'm actually going to concentrate on 2 of them. In the way that I present the comparisons between tools, I'm mainly going to be talking about the first 2, the see the data versus see the process dimension, and the technical versus intuitive dimension, although I will talk about whether tools are comprehensive or not. Since part of my reason for talking about this stuff is to talk about open software, I would say that open software tends to be comprehensive, kind of for obvious reasons, that there are a lot of people contributing to it. On the other hand, open software has a tendency not to be very consistent in design because there are a lot of people contributing to it. And even if there is one design philosophy, each contributor tends to have their own slightly different view of it. And you end up with a not very consistent product. Whoops. Okay, I've just gone the wrong way. So I just wanted to show you the framework. That's my quadrant. See the data over here, see the process over here, technical down here, intuitive up here. I'll come back to, a bit later, what direction counts as good. But for now, I just want to say that being in the top right-hand corner doesn't necessarily make it the best. There's a large element with these tools of horses for courses. Which tool you need depends on your situation. So since it's my own background, I'm going to start with Clementine, also known as SPSS Modeler. It's all about these visual process flows that you use to describe the process that you want to be applied to the data. The operations are these high-level operations or nodes. There's a design philosophy that everything has sensible default settings, so you don't have to mess around with the settings unless you want something different. It's relatively intuitive compared to other see the process type of tools. So in terms of its quadrant position, it's see the process, very much so, relatively intuitive, comprehensive. I have to qualify this, it comes in several modules, it's only comprehensive if you have them all, and it does have a coherent design philosophy. Maybe slightly less coherent more recently as they're trying to pile in too many features, but actually overall the design philosophy is pretty coherent. So let's put it on the quadrant. There it is, top right-hand corner. It doesn't have to be, we could change the scale and have it closer to the center, but you get the idea. It's on the extremes of intuitive and see the process. I am covering whether or not I think something is comprehensive just by the color of the dots. Next one I wanted to look at was SAS, and I should say I'm concentrating on SAS code. I've said SAS base, I probably should have said SAS code, because of course I'm talking about SAS coding when you've got all the modules. So first of all, it's programming oriented. When you write SAS code, you're writing a program. It is relatively high level. When I learned SAS and compared it with Clementine, I did feel that I was working with operations at the same kind of level. It's just that you write them as text instead of as a diagram with arrows. There tends to be a lot of technical detail. It feels that way anyway. So it's relatively technical compared to these visual flow tools. By the way, to be fair to SAS, it should be emphasized that they also provide visual flow tools. The thing is, they're not comprehensive. They're for particular purposes, and they don't form a complete toolkit, whereas SAS coding as a whole definitely does. So I'm kind of more interested in the more comprehensive, more complete versions of things. So the quadrant for SAS coding, quadrant position, is see the process. Fairly technical, I would say. Yes, comprehensive. Yes, coherent. So I put it here. It's kind of more towards the technical end. Because it's more technical and less intuitive, it's harder to see the process. You still can, and so it definitely belongs on this side, but it's further that way just because it's not so, the process is not so obvious. I could write my SAS code in such a way that you really wouldn't be able to see what order things were done in. And in fact, by the way, I probably could do that with Clementine as well, but it would be harder. Next tool I want to look at is KNIME, because it's the open, if you like, it's the open relation of Clementine. It's one of these visual flow tools. You can tell just by looking at it, it's more complicated, can't you? It's got several kinds of links. It's got several kinds of these things, which are called ports. It's just a more techie looking thing. It is a visual flow tool. And as with Clementine, it has these relatively high level operations, maybe a bit lower level than Clementine's. The settings tend to be a bit technical, and you tend to have to set them. It's relatively unusual in KNIME to be able to just use nodes without having to touch the settings. It's fairly technical to use, really. So where does it go in the quadrant? It's definitely see the process, fairly intuitive. It is comprehensive. It's a bit less coherent. There are lots of different add-ons that you can get, and if you start exploring what those add-ons are like, they're all slightly different. Well, it's not always inconsistent, but it quite often is. Good for all that. I've used it a lot. So here's where I put it on the quadrant. It's kind of in between. It's very much on the see the process end. It's a bit more intuitive than SAS code, I would say. Not quite so heavily technical. Next one. I thought I'd look at R. I've been using this a lot recently. As I say, most of my code looks a lot less understandable than that. It's programming, of course. It's very much a programming language. It's quite low level. This is actually using higher level primitives, but the higher level primitives, that shouldn't be a phrase, should it? But it tends to be highly technical, not really intuitive at all, I would say. There's a huge list of modules or packages, so it's very comprehensive. Each package makes its own design decisions, really. They all work differently. Although there is an underlying design philosophy, but each person who writes a package comes up with their own extension to it, and they're all different. Nonetheless, we love R, and here's its quadrant position. Definitely see the process. It's very technical. It is comprehensive. It's not really coherent. Fortunately, we don't show the coherence issue on this quadrant. And there are the 4 things that I've covered so far. I'm going to add a few more, but before I do, I thought I'd address a couple of obvious questions. First of all, why is there a straight line on this graph? How come there appears to be a linear relationship between technical versus intuitive and see the data versus see the process? There is a reason for that. It may be my bias, But the way I see it is this. The more intuitive something is, if it's a see the process tool, the easier it is to see the process. And so it's only natural that the further you go up, the more strongly it's see the process. You can see the process very easily here, a bit less easily here, somewhat less easily here, and it's hardest here, but it's still a see the process tool. It's coding. It's all about writing down the process. It's just, it's even easier to get tangled up in, we might say poor coding, but certainly a style of coding that makes the process less than obvious. Nonetheless, we are writing down the process, so it must be a see the process tool. So that's why there's this linear relationship. The more intuitive it is, the easier it is to see the process. Now, I said earlier that I would come back to this point. Is being in the top right always better? No, not really. And that maybe becomes more obvious after I've added a few more things. I honestly believe that this is about having the right tool for the right purpose. But I do think that we tend to forget, or some of us tend to forget, that the more intuitive tools let you concentrate more on the business issue. I have seen a lot of people who are experts in machine learning concentrate so hard on tweaking their algorithm that they kind of forgot what the model was going to be used for. It's not unusual. So the more intuitive a tool is, the easier it's going to be to think about the business issue. Nonetheless, the more programming-oriented tools have a big advantage, which is that they are more flexible. They can do more things than these ones, a wider variety of things. They're not actually the things that I spend my time doing, but some people do. For example, very different forms of data, very new kinds of data, that kind of thing, which may be why the data science movement has tended to move towards coding, because it's more flexible. What I'd really like to see is the data science movement, as it were, graduate to having to be able to cover the whole variety of data that it wants to process and still make its tools intuitive. That's my dream. I'll come back to that at the end. I thought I'd mention SQL. We all know and love. Not all of us love it. Very programming oriented, kind of medium level. It's a bit higher level actually than the coding tools I've mentioned earlier. It's really rather intuitive for a coding tool. It only does data manipulation, so it's definitely not comprehensive. And it is actually rather consistent and even elegant, some would say. So for a coding tool, it scores quite high. In terms of its quadrant position, it almost doesn't count because it's not comprehensive, but it's definitely see the process. It's kind of semi-technical. It's definitely not comprehensive, but it is coherent. So I put it kind of over here where it's still coding, so it's down here in the lower, more technical side, but it's kind of at the upper end of that. And I just added a few more things. I thought it was only fair to say that SAS-EM, if you ignore the fact that it's not comprehensive, it's quite close to the most intuitive tools. Over here, I've put Excel because we use it so much. And I've also put in Tableau. I don't know if Sophie's still in the room. Anyway, if anybody else here is a Tableau fan, I very much hope they're not offended by what I'm saying about Tableau here. My point here is, I do actually think Excel is very intuitive. So it really scores very highly. It really only does simple things intuitively, but for those things, it's very intuitive. You can use Tableau for much more complex things, but it's really hard to understand what's going on. Actually, it's hard to understand what's going on with either of them. when you're doing complex things, because they see the data, not see the process tools. So once you've got your beautiful visualization in Tableau or your complex spreadsheet set up, it's great as long as it works, but if there's anything wrong with it, it's really hard to fix. Okay, I don't need to keep walking across the stage, I can just use this, of course. I'm moving into my last section, which is about, could we move open analytics software up that ranking? It's not a ranking, but could it do all the things for me that Clementine does, for example? So I've highlighted in green the open ones. And notice that you can kind of pair KNIME with its commercial neighbours and R with its commercial neighbour, and I'm not sure how to classify SQL in that respect. They're kind of generally less intuitive, less consistent. You can see the process, but not as clearly as their most similar counterparts in the commercial world. So what could we do about this? Well, actually, before I try to answer that question, let's try and explain why it is that way. Why are open tools more technical and less business friendly, less intuitive? I think this is the reason. Commercial tools are driven by selling. That is to say, the thought process has to be around someone's business problem. And their survival, the very survival of the software, if you think of it as a thing that has to survive, depends on fit to the business to which you're trying to sell it. So it has to be a good fit. On the other hand, open software is driven by programming. It survives because people want to add modules to it. It's interesting to program. That's what its survival depends on. So it's, I think, those two different thought processes, just driven by what really makes a piece of software live past its inception, that cause these differences between open and commercial tools. Now, could we do anything about it? Could we have one of these? That's not to say that I'd replace all of the others with this. I certainly like R very much, for example. But wouldn't it be great if we had something that was truly intuitive as well? Someone's doing a little dance at the back. Is that 0 minutes? Okay. So it is. Well, I'm nearly finished. Thank you. Thank you all for listening this long. Or must open software always be techie heaven? Something that programmers like but nobody else does. Well, challenge one, I'm coming to the end here. Challenge one, how can we have a business orientation in open software? Maybe it depends who does it. I'm not sure. I'm really putting this on the slide to raise the challenge. How can we have open software sensitive to the needs of the real end users? And challenge two, how can we avoid these design messes that people get into when you've got lots of people spread over a wide population all contributing to the same software? I don't know the answer to that, but I do have a kind of dream open data analysis toolkit, and I thought as a last thing I'd share that with you. What would it be like? I'd like to see it based on one of the existing ones. I'd like to see it built up from something like R. It doesn't have to be R, but something general and programmy. And I think it should be built up in 2 stages. The first stage would take it to those higher level operations. So if you write in this intermediate level language, it would kind of look like SAS, only without the technicalness. It would look like high level operations which are linked together in a very simple and intuitive way. But it would still be a programming language. That's actually useful because if you can print it out as text, it's much easier to kind of take away and read, to debug, to get somebody else to debug your code. So that would be my intermediate level. And at the highest level, I'd like a visual flow tool. Based on that intermediate level kind of cleaning up. And you can imagine that this tool, there's 3 ways of reading each analysis. One is as a high-level diagram, which is useful to just kind of manipulate and use as your working tool. One is an intermediate level language, which is kind of good for debugging and also good for taking away and reading on the train. It tells you something about my habits. And one, and the lowest level being the raw, as it may be, R code, which is actually what's executed. One reason for keeping an existing execution engine underneath is that they are actually really good. I mean, I'm so impressed with R in terms of its efficiency. So I wouldn't want to throw that away and say, no, we have to build that again. I like what it does. I just wish it was expressed in a simpler way. And that's my talk. Thank you very much for listening.